Welcome all. My name is Frank Crawford. I am the Education Committee Lead with Passive House Alberta, and welcome to this month's Coffee Talk. Today we are hearing from Tyler Hermanson, who is the Director of Innovation with 4 Elements. Tyler is an architectural technologist by training and a longtime energy advisor with over 15 years of experience in energy efficiency, sustainable home and building. Over the last 4 years, over the last year or two, I guess, 4 Elements has led a team of high-performance renovators and builders with funding from SSRIA to perform some deep energy retrofits on 3 homes in Calgary, including his own home. And that's what he will be talking to us about today. DERs is what the acronym we use for deep energy retrofits, if you see that throughout the presentation. A little bit of housekeeping. If you have any questions, put them in the chat box for now. We'll leave the questions to the end. I'll either moderate them or you can turn on your mics at the end to ask the questions. And for next month's Coffee Talk in April, we will be having HVAC systems, and they will be showing us and talking to us about the new to North America Passive House certified CASA series ERVs from Swagen. So with that, I will let Tyler take it away.
Cool. Thanks, Frank. Well, welcome everybody. Thanks for joining us. Yeah, so we're talking about deep energy retrofits. Frank did his little introduction there, but yeah, I've been an energy advisor since 2006. I've done lots of energy modeling and consulting. Took the first passive house course that came to Alberta. I think that was 2014, 2015, and got very excited about passive house and have done some passive house designs and some passive house testings. None of those projects certify. That's a different story, different problem, different presentation maybe. Today we're talking about renovations, deep energy retrofit style renovations. We'll talk a little bit about what that means and how I've defined a deep energy retrofit as opposed to just a renovation, and the kind of steps that these houses go through. And we'll talk about our project and the 3 houses in our case study that are just finishing up construction now. We finished our milestone 2 report here just the other week. We're combing through all our data now. So this is looking at our construction photos from through the summer, fall right now. So we know that all homes are aging. As soon as we build them, they're deteriorating, and there's a burden on homeowners to maintain. So that's baked into home ownership. We know that's coming. And often we're just renovating. So we're taking something that's aged, like a kitchen or a bathroom or a mechanical system. We just renovate it. We're restoring it back to new condition. When we talk about a retrofit, this is really a gut renovation or a major rehabilitation where we take something right back to the bare bones and build it back to even better than new construction. Often a retrofit, in a lead gut retrofit, you're going lead. In our case, we're focusing on the energy system, so envelope, mechanical, and we leave the rest of the house alone. So the kitchen, the bathrooms are all left as is. This is, different than a gut renovation. So when we talk deep energy retrofits, we're looking for a specification or quality of build that's kind of ready for 2050, looking ahead at the new tier codes and looking ahead at energy needs of the future. So we focus a lot on energy savings and substantial improvements in comfort. And we also certainly had our eye on carbon savings here, both in operational by reducing our energy needs and adding solar panels, but also we're looking at embodied carbon. But very quickly we realized as a renovation, by saving these old homes, we're so far ahead from an embodied carbon standpoint. The 5 or 7 tons of carbon we embodied in the new siding and new windows really isn't a big deal. We save 50 by maintaining these homes, saving these homes. So this is our project. It's hosted here at SRIA. We are project 10, and our project findings and reports are available as they're published there at SRIA. So the goal was to take 3 houses through a deep energy retrofit with various approaches and use them as a detailed case study. So costs, process, photo documentation, and energy monitoring pre and post renovation. So we really took that house as a system approach to try to make sure everything was going to work together as a system, that the walls and the windows were going to work. We were balancing heating and cooling. We were adding ventilation as we added air tightness. Everything's connected, and make sure the house works as a system. So major components we looked at, certainly the envelope was the place we started. Improve comfort, reduce energy, add air tightness, combined with good ventilation. The three projects took different approaches. I'll talk about here in a minute, but very quickly we locked in on that kind of R27 to R32 type range. That is just kind of the sweet spot in the performance curve for insulation. That's you're just ahead of diminishing returns there. And we knew that air tightness was a big opportunity in these old homes. My house started at 8 air changes. One of the other houses was 5 air changes. That's a lot of air leakage. There's a lot of energy being lost through the gaps and the cracks and unfinished air barriers from over the years. And so that was a major focus. And looking at windows, is a big piece of the comfort as well as energy savings. On the mechanical side, 2 of the homes went with high efficiency heat pumps, air source heat pump heating systems. So took out the old furnace and went with a heat pump, and heat pump domestic hot waters were the preferred choice for the 2 projects. So gets them onto an electrification. Could get rid of the gas line with very efficient equipment. There's some nuance to how these systems go in, we found, and renovations make it a little bit more challenging. Something like an air source integrated heat pump hot water tank like this guy here, they're quite a bit bigger. And so we learned real quick that where you tuck them in matters, and the fan load, the fan noise that you get off these units, or the pump noise that you get, because it's basically got a little compressor like you'd have in a deep freeze or refrigerator that's pumping heat into the hot water. Well, that runs 4 or 5 hours a day as it's reheating the water, pulling heat from the house, because usually we have some extra heat in the mechanical room or the laundry room, and we can dump that into the hot water. But we noticed the comment that the rest of the house is so quiet now. I hear this air source heat pump or this heat pump hot water tank a lot. Does it have to be so loud? And so we got some feedback on those. And solar panels is that crowning piece. The applicability of solar to the 3 projects varied quite a bit. One was a really good candidate. One was not a great candidate. One was kind of in the middle. We have existing homes with complicated roofs, concrete tile roofs. One of the projects had a lot of vegetation overhang that was worse than we initially thought and cut into some of the generation. So solar is that final piece of these deep energy retrofits. So project 1, this is my house. It's a 2-story with a walkout basement built in 1954. Was renovated in the 80s, and then my family started renovating it in 2000, and my wife and I renovated it again in 2014. This is just an ongoing project for us. It does have a secondary suite, and that adds a little bit of load to the home that you have to account for in a deep energy retrofit. That tightened up our electrical demands and things like that. When we started, the house was heated by a combo boiler that we put in 2014, and basically had very poorly insulated walls. Originally 1954, there was no insulation there at all. In 2000, we added 1.5 inches, which got us effectively up to about R11 overall. Not a great R value to start with. Ceilings kind of ranged R15, R44, depending on the spot we were in. Again, as you renovated over different times. The basement, we had gotten pretty good insulation on. We got it up to R23 in the last reno. And the air tightness even surprised me. We had tested the house various times over the years for practice or for training, never done an official 2 blower door double zone test with the secondary suite. And so to finally sit down and do that, which is silly when we could do it anytime, was surprised even me that it was as bad as it was. I knew it was bad. I didn't think it was that bad. So we're sitting at 33 gigajoules per year when we started. So worse than a typical code house by a fair margin. Most of our heat loss and our energy consumption was in space heating. So most of our fuel consumption was natural gas. We kind of look at the projects on a viability list that the builders and I put together. And my house was the worst candidate. It was complicated. It had a complex yard. It had 3-story height on one side, so it made it less safe to work around. And so, I kind of gave it a poor score on the retrofit ready kind of checklist. After working through this checklist a few times, though, I took off built prior to 1980. I didn't mean it to be like a go, no go kind of decision, but we talked about it, and renovating a 1980s home would be very different than renovating a 1950s home. And so we wanted to classify them differently when we did these assessments of a house as it came in, whether it was a good candidate for a deep energy retrofit. So it's not really the age that's important, we found, but that does affect your approach quite a bit. The second house in our study is split level, built in 1957, so a little bit bigger. Mechanically, it had been updated in the 2000s, but again, not a very well insulated wall system. Ceiling and envelope was a little more airtight, was less complicated, had been renovated less, and made it a little bit easier that way. 134 gigajoules, so very similar to Project One in terms of energy. Much better candidate on our viability scale. The only problem it had was a lot of trees around it, inner city neighborhood, taking away some of its solar access. And we did find it had asbestos in the drywall mud, which just complicates your renovation a little bit, something you want to be aware of. Project 3 was a little bit simpler house. It's just a bungalow, 1955. It had been interior renovated over the years. It was in, very good shape interior wise, but older mechanical system. So a 80% efficient furnace, probably from the early 90s. So end of life. Older hot water tank, also at end of life. A little bit more insulation in the walls, but again, a pretty poorly insulated envelope and pretty high air change, typical for homes of this kind of vintage. A little bit bigger home had a little bit higher energy footprint. It was a very good candidate for a deep energy retrofit. We had a nice big lot. We had lots of working room around the house, simple roof with good solar access. The hazards had already been remediated and we didn't have any impacts there. So kind of gold star project for what we could do. So the projects all took different approaches to the deep energy retrofit. Envelope, we had a mix of windows, had a mix of mechanical systems, but the walls was the biggest difference between. Project One wrapped the house with 4 inches of new next gen insulation XPS, new generation XPS, for an R20 wrap on top of the R11 that was there, plus the newer walls that had been insulated with various R12 or R20. Project 2 did a EFIS stucco approach, so 8 inches of EPS foam added on top of a liquid applied air barrier, and then an acrylic stucco applied. And then the third project did a new double stud wall, kind of a prairie style wall, strapped and girded out from the house 8 inches, and that was filled with blown cellulose for an R30 wrap. So this is probably our best insulated house at the end of the project, but they were all pretty close into the 30s kind of wall R value range. So we got a good comparison in the 3 houses. So the XPS installed in 2x8 blocks. So it goes on pretty fast. And we kind of temporarily glued it to the wall with a bit of foam adhesive, and then did a taped air barrier system. So we're moving our air barrier out to the outside plane with the Owens Corning joint seal tape. All the transitions, all the tapes. There's a lot of little things that need to be patched up when you go to an exterior air barrier like this. And then the whole thing was strapped out so that we could apply siding, just a wood smart LP siding. Project 2 went with the liquid applied. So this gets painted basically over, thick paint almost, going over the original plywood, over the details. Lots of work kind of meshing that and taping that, making sure I've got a good airtight base. And then you adhere blocks of foam on top of that with a drainage plane, and then do a stucco EFIS around it. And you can see we insulated the crawl space with 4 inches of XPS foam as well. So looking closer here, you can see the little plywood girts that hold these stud framings at that 10 inches. I guess it was 10 inches. And you've got to do a lot of work extending everything, right? So all your electrical plugs or light plugs for the outside move out 10 inches. Your HRV ducts and those things all move out 10 inches and get adjusted. But then you wrap it with mesh and just pack it full of high density cellulose. So this had kind of the lowest carbon footprint of any of our projects, and it's very quiet now with that kind of insulation in such a thick wrap. Makes a huge difference to acoustics. So once you've got it netted and blown, then you quickly wrap it with a house wrap type product. product, that becomes your air barrier. So this was taped and sealed at the edges to make the official air barrier was the outside face of the tie par, taped and sealed. Made for an awkward transition up at the attic gables. So we worked with the city and got approval to remove the eave ventilation for the first 4 feet of the roof and moved our low side roof vents to new roof vents sitting above the new thick insulation, and then a high ridge vent higher than that. So there's still attic ventilation high and low. We still met our 1 in 300 building code ventilation, but really that 24 inches of insulation, which is quite a big area in this low heel roof, gets unventilated to make sure we didn't get problems with ice damming because of thermal bridging at the rafters or something we missed. The first 6 feet of the roof now has an ice and water shield. Actually, I think the whole roof ended up with an ice and water shield just to make sure nothing was going to make it past the shingles if we did get ice damming. We haven't had any problems with it this winter, but we're still testing it out. So we're kind of comparing the different approaches. The numbers are still being crunched, I'd say. It's all very fresh. I think the costs are actually going to be pretty comparable. Like they're all about the same. There was no huge winner loser. I think when it comes to sound dampening, we definitely noticed the best result with a cellulose wall. In terms of being narrow, definitely winner goes to the XPS just because your insulation level is so dense at R5 per inch. But we're looking at labor costs and we're looking at material costs, and we're going to issue a paper outlining all the construction costs of this project. So that's a big part of our deliverable we're working on now. On the mechanical side, I mentioned the integrated heat pump hot water tanks, and then we have air source heat pumps. So you have an outside unit moved to the outside of the house, usually in the side yard there, and then you had a forced air indoor unit. Project 2 really had the opportunity to take the whole furnace now, because it didn't need a chimney, didn't need any venting, and they moved it into the crawl space, nicely finished laminate floor crawl space that we insulated and worked on at the same time. And so now they opened up quite a bit of floor area to have better use in the basement. So that whole mechanical room got moved into the laundry room. You've got a nice big laundry room space instead. So you're getting better use of square footage really with this. But we still use the original ductwork. We were able to make all that work. So some of the rules of thumb, I think we started to develop this is certainly if you're going to touch something in your reno, you got to make it right. For 2050, it's got to be try to make it right for you'll never have to touch it again. It was so frustrating in these renos in all three cases, we had stuff where we were going back, our homeowners were going back to renovate stuff they'd already done once, but didn't do enough or didn't do it right. In my own case, we added that 1.5 inches in 2000. We could have added more then, but we didn't go far enough, or doing work, air sealing work, and having to do it better because it didn't get far enough. The risk really in doing a regular renovation, we really found was you're locking in inefficiency if you're not careful. If you install hardy board siding on top of an uninsulated or poorly insulated wall, not enough insulated wall, you're never going back to that. The hardy is locking it in because that's a long-term finish. It's going to be there for 30 years maybe. And so in the end, like our project, we started to get tight on budget. We didn't have enough budget to insulate and re-roof to a 2050 type quality that we needed to hit and remove and replace those concrete tile shingles. So we decided not to touch it. We left ourselves a transition plane. We'll be able to come back and tie into that in the next phase of our reno. But we couldn't do the roof right. We couldn't get it up to R40 air sealed and fix everything properly with the budget we had. So we had to phase it out. Complexity requires coordination. There is a lot of moving parts. They feel like small renos because they're only $100,000. You're just doing the exterior maybe, but there's holes, there's trades to organize, and there's a lot happening, even if it's for a very brief few-month period. And so certainly realized coordination needed to be tight, communication needed to be very good. Becomes a problem if you can't get your supply chain sorted out. And this was a tough year to be doing this with supply chains. We did have some stop and starts as we waited for things to arrive. I think we overall did a pretty good job. So that's the projects that we did. The case studies are being worked on. All the results are going to be there as part of our shared deliverable with Saria. Another lesson learned was pre-finish, pre-checking your air tightness. So when your envelope is still exposed, so you can see here smoke being drawn in to a mist tape seam. So as the next year air barrier, that tape seam is really important. And even little gaps leaked, and you can see smoke being drawn into the wall in that corner. So all three projects, we did a bunch of blower door testing during construction before you started to side or cover those air barriers. And that was a really good, important piece, I think. Would have been very easy with these complex envelopes to miss something, clad it over, and not be able to go back and seal it. So you check everything carefully before you get too far. So everything will be available at Saria. So all of our construction photos are posted there, or will be available there. Our case studies will be there. Our costing report will be there. Energy monitoring data will be there, because we really wanted to sell this project as a go-to for stepping stone for other projects to pick up the ball and use to develop their own course material or marketing material or case studies or websites or whatever comes next. So all the data that we developed is there. People can digest it and use it how they see fit. So we're into milestone 3 now, which is the data monitoring and final case study reporting, and we'll be wrapped up by the fall. So lots of stuff still to do, but lots of lessons learned so far. And now you guys are caught up in everything we just done.
So we got a few questions that were sent in beforehand. We'll go through a few of those. If any other questions, feel free to put them in the chats or put your hands up. I think one of the interesting ones were kind of talking about all the retrofits you guys did were outside retrofits, working from the existing wall out. Maybe just talk a little bit about maybe if you want to do a retrofit working in, or just the different types of walls, different types of retrofits.
Yeah, I think there's definitely a lot of different ways to do this. Going and doing your work on the outside is definitely your preferred method. It's less invasive, less problematic. And we actually didn't find any problems going out with building code or city bylaws. There is enough latitude in both of those codes that you can thicken up your walls in most cases. But if you're really stuck, wanted to do an interior reno, I mean, the math still works. If you add a bunch of continuous insulation on the inside of your studs, you get the same effective R value. You get that thermal studs and things like that. You're just losing more square footage. And a lot of these houses, 1954, they were already pretty small, and storage space was at a premium. And so you can't afford to lose square footage. If you start to mix and match and you do one wall one way and another wall another way, you're going to have to pay really close attention to your transition details. We found a couple spots where we could have easily missed an air sealing detail just because the plane changes. And if you're not tight on your trades and you're not watching the mid-stage construction blower door testing really carefully, especially in a reno when things are so complicated and there's abandoned piping in the walls and there's old wiring or something you didn't expect, just so much variability in renovations. You just have to be careful. That's again why going to the exterior and keeping your whole plane of air tightness on the outside of the house, it's easy to work on, it's easy to see and even visualize what's happening. And you kind of move through the system that way.
Maybe we'll start with, I guess, a bigger one. So I guess, what are the big things that you see kind of holding back the adoption of passive house or high performance buildings or deep energy retrofits and kind of the larger market? We've obviously got past the pilot project. We know it does work. These are more pilot projects for deep energy retrofits. How do we start scaling now, I guess?
You know, and I think it's the challenge we've always been having is awareness and cost. So we keep working on making sure homeowners are more and more aware that these solutions are here and that they're doable and they're not laboratory research projects. They actually are, just off the shelf products installed maybe in thicker quantities, but it all works. It's all been tested. So that awareness is really important. And the cost is the second piece. These are not cheap and easy renos. The minimum for our projects looks about $100,000 budget. A lot of that is innovative energy efficiency type stuff, but a lot of that is just maintenance, new siding, new maintenance to a degree is just the cost of home ownership. And if you're going to do a envelope retrofit, you're going to replace and renew a bunch of materials. But that's a chunk of capital that a homeowner needs to have at hand. And lots of homeowners are going to dip into their home equity. And that's an option for people who've been in their home for a long time. For others, you're going to, you have to look for line of credit and those types of things. We found that as a big barrier. and adjusted the ability to do some of these renos. So now that we have the SEEP funding coming out and we have the Greener Homes loan, that's a smart program. That's what we needed, is in order to be able to give homeowners access to the capital, be able to do the reno properly. And so between the two programs, I think you get $70,000 loan right now, low interest loan, low-ish, and that's pretty valuable to homeowners.
Brian has a follow-up question, just talking about the ability to kind of reuse ducts, or do you have to change anything in ductwork when you are going from natural gas to heat pump, and I guess trying to integrate your ERVs or HRVs?
Yeah, it's a good question, and it certainly, HVAC in general is something we need to be looking closer at in residential. We're doing a study right now with the Canadian Association of Energy Advisors to look at actual installed furnace flows and duct pressures and see if there's commissioning problems in the residential furnace sector. And I suspect we're going to find some problems. In these particular projects, we did end up using the existing ductwork for all of them. And that still worked because we had reduced the load so much. The CFM that we needed to push through was no greater than what was there already. I think a careful duct design is valid, though. We did a room by room heat loss calculation, so we were being careful in some of the math, but did that fully translate into careful sizing and checks by the HVAC team? I think that's a place we could do better. And we have to make homeowners aware that, a fan coil doesn't deliver as hot an air, so it's going to run for longer. You're going to feel that draft from the register more, and it's not going to be warm and fuzzy necessarily. But the home's heat loss went from 15 kilowatts down to 5. So there's a pretty big difference just in how much that fan coil delivers anyway. And that's the big opportunity. Careful check of that ductwork as well. You have to make sure everything's still connected. You don't have asbestos in your mastic or something like that should be remediated at this point. You're going to find lots of ductwork where things have been deadheaded or modified in some way, and you've got to make some adjustments. We had to add a couple registers, and we had to add some ventilation ductwork to the projects to kind of make it work to current standards.
Two questions. Is there any programs for an owner of a apartment building to take advantage? And my second question is that we're looking at building basically a passive house, but I'm looking at really low technology for it. So a lot of people have done the airship houses where they use the earth tubes for cooling. Anybody dabble in that with a passive house?
Yeah, so the first question on the multifamily, there isn't as much funding available for landlords in general. I think all of the rebate programs I'm aware of right now apply only to owner-owned units. Even the Greener Home grant and loan is tied to multifamily that you live in yourself primarily. So it does create a gap in the funding parameters for landlords. Frank, do you know of any others for landlords?
I think once you go into commercial or multifamily, you have a little more access to other types of funds. Like there's other companies, I think I always mispronounce it. I think it's like Sofiac or something from Montreal that are kind of providing energy improvement as a service. So what they do is they go and do a energy audit of your larger building, and then kind of take those savings, finance those savings on a type of mortgage to kind of reduce the capital upfront cost. So there is definitely not as many, but they're kind of slightly different. They're more in kind of the more open market.
And the MLI Select program from CMHC does apply to landlords. And I forgot, it does apply to retrofits as well. So the MLI Select program is, a guaranteed insured mortgage for those construction costs or renovation costs. My builders have been telling me it's a pretty valuable program because it reduced their lending costs so much when they're doing these high performance new homes or potentially renovations. So you'd want to look at MLI Select probably as a multifamily building.
And did you want to talk to the earth tubes and their uses for preheating and pre-cooling that you've seen?
Yeah, I haven't seen a lot on the residential scale of that. And you have to be really careful with your indoor air quality. So you don't want them to pick up soil gases or radon and pipe that into your house. So you don't want a direct ground to air connection. You just want the heat. And so that's more often done with loops, and you run glycol through rather than direct air. so that you're just fully separated from a safety standpoint. I don't even know how to do the math on that. So a lot of that stuff, the math gets really tricky. And PHP does a little bit of that, but our HOT 2000 software we primarily use doesn't even understand that system. Wouldn't be able to calculate it. You'd have to go a little deeper with an engineer.
Yeah, there has been a few, and yeah, to Tyler's point on space, most of the times we've seen it used are rural acreages where you have lots of space, because generally your earth tube, you want about 100 feet of length, you want it about 8 feet down, and preferably, well, obviously it has to be sealed, but preferably no bends. So it's hard to do that in an urban lot. Actually, if you go onto the SSRIA website, there is another project there funding the Métis, a Métis building way up in the north, and Trevor Butler, who's one of the best people probably doing earth tubes. He's out of Kelowna, but he was the engineer on it, and they have earth tubes as well as some other ground exchange. So it can be done. Generally, it's done in rural or in larger buildings where you have more space. But yes, definitely want sealed.
Rob Avis and Verve Permaculture has been doing it on some of the greenhouses they work on. That's not a house, but the theory, maintained. So using earth as a battery, using airflow through that to store heat and return heat. And so they've been having success with that in the greenhouse side of things.
I guess you just want to go a bit more about the air source hot water heaters, kind of the robbing Paul to pay Peter, how they are still useful.
Yeah, the modeling does increase your space heating because you're pumping heat out of the house into the hot water. So it sees that winter draw of some extra thermal energy. But for most of the year, really there's extra heat in the house, all summer, that kind of thing. And so the net efficiency is still quite high. The ability of these pumps to pump it higher than 1 COPs throughout the year is pretty good. That's how they get such high efficiency and the net win. And the modeling and the research that Enercan does give a high return, a good energy efficiency to these systems. Now, it used to be very cost effective to buy these heat pump tanks, and the prices are quite variable now. So you'd have to watch it. At a certain point, you pay too much for a tank for what it saves. We always look at things in a dollar per gigajoule kind of way, or dollar per kilowatt saved, and kind of make sure you're chasing the most cost effective savings first.
Price does really vary. I've heard from other builders that the price of just a electric hot water tank has gone up so much that the heat pump hot water tank ended up actually being almost the same price. So it really varies. Generally try to do a larger tank than you would normally so that you can stay in heat pump mode longer. Mm-hmm. And from an electrification point of view, try to get the 15 amp 240 volt tank, which is even harder to get. So you really got to order that earlier, just because it has a smaller electric resistance in it, so it doesn't need as big of a breaker on the panel.
And you have to plan for where that ejective cooler air is going to go, right? You don't want to shoot that into your living room. You need to make sure the room has enough heat in it. So often it's tied to a room that has a big return air pickup for the furnace, so that it's drawing in that cooled air, heating it up through the furnace, or mixing it in with the rest of the house there. So you don't get a room that's super cooled. Not that it ever go that cold, but if you put a heat pump hot water tank in too small of a room, it's going to really chill that room down. Jordan, you had a question on tankless type hot water systems. Certainly we have seen those in use, and we're seeing them in some of the net zero homes as well. We don't see the electric tankless very often, and that's really what we would have needed in these projects, because we were trying to electrify and get off the natural gas. We were finding that through the envelope savings and the heat pumps, we were getting the energy consumption so low, the amount of natural gas we would have used in a hot water tank would have been so low that it didn't make sense to keep natural gas. If you're not using 20 gigajoules of natural gas a year, it's pretty hard to justify that connection, that monthly fee and everything else. So that can push projects with very low demands just away from natural gas, including tankless at a certain point.
Yeah, the connection fee for natural gas was kind of somewhat stable at $400 for a fairly long time, but now it's starting to go up to, I think, $475, approaching $500 in Calgary, and in Edmonton, I think it was $650, approaching $700. So if you want to get off gas, you really want to get all the way off gas. You don't want to leave just that little bit of leftover and still have that connection fee.
Tough to hold on. ATCO's working on a new low consumption rate, which will lower that a little bit, the ATA rate. I still think you need, it doesn't really pay unless you're down pretty small. And then you're just close enough to go that little bit further and get off gas entirely. So it's going to be like a little bridge thing, but you can see everybody trying to figure out what's the kind of sweet spot right now. And it is hard for us to find that now because there's just so much happening in the energy cost side.
But yeah, with a unit, when you're using a tanked heat pump hot water tank, you really got to watch the size, or maybe even duct it to have enough space to take heat out. Otherwise, it will make a room colder. The air source heat pump is all from outside, so that doesn't really have an effect on the room it's in.
Yeah, basically just, we're looking at a air source heat pump hot water heater. Currently the tanked water heater is located next to a gas furnace, which creates a significant amount of waste heat. But I'm concerned that if we switch that out for an air source heat pump, that there won't be enough waste heat in the utility room to supply the hot water heater. And that utility room and the garage are unheated, and they already get close to zero in cold winter temps. So just concerned about, whether that's viable or if we're going to end up freezing those rooms.
Yeah, if you don't have a good warm room, it won't work the way it's supposed to. So you might have a kind of a unique case that needs to be looked at more closely.
However, most of the heat pump hot water tanks can be ducted, so you could run ducts from where it's located to and from other locations, and then you could put some acoustical isolation in those ducts to still use the heat from somewhere else. Like if depending on the house, you could duct it from the peak of the roof, pulling that heat down in, and then exhausting the duct if you're like somewhere more rural into maybe like a cold room that wants to have a cooler temperature, then finding uses for the energy and the temperatures that are produced.
Yeah, for sure.
I guess one question, maybe with foundations, did kind of your optimization that you did on these projects show how important the insulation below grade, like 1 foot down versus all the way down to the foundation? And even, I guess, because it was fairly innovative, maybe talk a little bit about the ways that we have found to actually do that excavation around the foundation.
Certainly in the modeling, we found unless you insulate all the way down, insulating 1 foot or 2 foot down just doesn't have any savings. There's just so much flanking heat transmission through that whatever portion you leave uninsulated up the concrete around your insulation, it erodes that effectiveness quite quickly. So it seems to be kind of an all or nothing. Now Hot 2000 is not the best modeler of thermal flanking transmission, and PHP and therm type modeling are much better at, but it wasn't the scope of these projects to look at that. So we did put exterior insulation on the exposed parts of the foundation. Project 2 went all the way down there, a shallow basement. We're there. We know that there's some savings if you can, and it helps, but the math gets really complicated. The opportunity we found, we're trying with Project 2, was that we hydrovac'd a little trench around the whole foundation because we only had to go down 4 feet and the soils were really good. And so it actually wasn't that expensive to hydrovac and then drop in 4 inches of foam down to the footings and fully insulate it that way. I think we kind of have to see how that works. You don't see this a lot. PS should really be put in air cavity when it goes below grade, just to make sure it doesn't slowly absorb water over time, because it is very resistant to moisture, but it's not 100% impermeable. It will absorb water over periods of time, and that's going to erode your R value. So maybe backfilling with drainage rock or something like that to help keep water away from the foam. And it wasn't a great opportunity to improve damp proofing. So if you have foundation water issues already, this isn't going to help you because that trench isn't deep enough to really fix waterproofing properly. This was to add insulation and deal with that only. So I think there's some more research to kind of do best ways of dealing with foundations. The big caveat is whether you already have weak waterproofing or you have water issues already or not. And if you do, then we got to fix those fully and properly, separately, entirely from the energy side of it, because some of the solutions aren't going to do both jobs.
There was another question, kind of a little bit about prefabrication or offsite construction. So I know Saria is also sponsoring some work of Peter Amarangan up in Edmonton. Do you want to talk a little bit to kind of any of the costs or learnings that we've got from Northern Peter?
Yeah, the competitive approach is manufacturing new wall panels to wrap around the existing house, the inner sprung approach from Europe. And I think there is opportunity there. Peter's had success now on single family homes. The challenges are certainly, this is a fledgling industry, and the accuracy that they need for manufacturing the panels has led them down this really cool technology using drones and computer generated measurements to get really accurate panel sizes. So you need all that to really make this fly. But there's a big ramp up, I think, for that to be spread more widely. It's not in the manufacturing of the panels. That's easy, and lots of people are doing panelized walls and flying them in place on new homes and flat building decks and all that kind of thing. No problem there. But getting the measurements right is the huge challenge. It's one thing in Europe where you could have 100 units that are identical that were built in the 60s and 70s, but here there's just so much variety to our housing shapes and typology. Getting really accurate measurements down to the 16th of an inch really to make a door fit properly is super big challenge to that approach.
Well, I guess maybe talking a little bit about windows and kind of what windows and what performance was selected, and whether or not kind of windows make a financial sense or it's more just a comfort improvement.
So we definitely replaced the windows in these homes, and Project 3 really tried to argue that they could keep two of the windows that were replaced in the last few years, a good low E double glazed unit, and they really couldn't. Right away they noticed the difference in those windows and how they felt and how drafty they were and condensation on those windows. And you're like, nope, nope, nope. Before we get too far, they quickly ordered replacements for those as well. So if you're going to do the windows, you're going to do all of them for sure. We learned that even if they're fairly new, they just probably aren't going to be good enough for a deep energy retrofit. So the windows kind of ranged. We did kind of locally, casement style PVC made here in Edmonton in Alberta. I think they were a 1.97, one kind of U value windows. And then one of the projects, Project 2, used Innotek's tilt turn windows with a little bit better U value. I think they went as low as 0.8, 0.9 something, I think, on those windows. Much tighter. They close much tighter than we noticed on the casement windows. But in both cases, it looks like the cost for windows, don't make it a big energy saving financial upgrade. It is there for quiet. It is there for comfort. You're updating the look of the house and that kind of thing. So you want new windows to go with that kind of thing. But the financial drivers are really never going to be a strong argument, it looks like, for a deep energy retrofit. I think the best we're going to be able to show is maybe a 2% return on investment. You'd be better investing in mutual funds for sure if you just had this cash sitting around. And that's not the whole story. And I think as soon as you start to dig deep in the financial payback and all the calculations you can do, for most homeowners, you kind of lost them at that point. It's a better return on investment than your trip to Florida. Not as good as your mutual funds, but you get a lot more out of it. And the value that you get from these deep energy retrofits in terms of comfort, in terms of carbon savings and energy savings are I think, better justifications. And people are going to do it for those reasons.
And I guess there was air monitoring and CO2 monitoring in the houses. Have we been around long enough to, or they had the updates long enough to see any improvements in like relative humidity and air quality, or not quite yet?
It's hard to see in the data. It's really hard to see. Things just move so much in a house, depending on how many people are there and whether you're away for a weekend and, just what's going on. So I haven't seen a dramatic change. In the energy monitoring I've seen so far, I see a little bit of a narrowing between max min temperatures. So there is a steadying of the temperatures. We are monitoring air quality as well. So CO2 is kind of the biggest marker we're using. And the HRV helps a ton. Obviously, that makes a big difference. State is working on that part of the data monitoring and analysis side, and we just haven't been able to dig in deep enough yet, because there's just so much data there. It's going to take some real data mining to figure it out. So it wasn't immediate. I think maybe that was the biggest surprise, is that the energy savings, the temperature differences weren't like immediately in your face wild. Yeah, the house is more comfortable. The house is definitely quieter. It's hard to quantify that just day to day. So it's better and it feels better, but you don't know by how much. So we'll see once we start digging into the now 1,000 line spreadsheets. we'll start to see some trends, I think.
Oh, a good question about the heat pumps. So do you still do your nighttime setbacks with the heat pumps, or do you have to run them a little bit differently, or are we still figuring them out a bit?
I think we're still figuring them out. The homes definitely don't cool down as fast, and so you don't get the same benefit of a nighttime setback. And then the heat pumps take quite a bit longer to come back up to temperature. So I think all of us have gone away from setbacks and just let the house run, set it and forget it type thing. So it's a good question. I'll have to ask the homeowners, see what they're running right now.
Yeah, that's definitely what we found in my passive house, is that now that you don't have a giant jet engine in the basement that can warm up the house in 10 minutes, you have a smaller unit, you just let it, set it and forget it, leave it at the temperature that you like, and don't touch it.
The ductwork is, these fan coils are loud. There's still a big fan running. I think designing for quiet was a missed opportunity, really. We need to look closer at in deep energy retrofits, because you had a forced air furnace already, and so you're like, okay, we're just going to put forced air in again. You don't really realize, though, how much quieter the rest of the house is going to get with all that insulation. And so suddenly now you're noticing the ductwork more, and we need to make sure that we fit the systems to that carefully. And maybe there's some opportunities when you're replacing the fan coil to put sound dampening in and make it even quieter than it ever was before.
Question about possibly having an airtight wood stove in deep energy retrofits for kind of those cold climates or those really minus 30 days. Any thoughts on that?
Certainly in the net zero program we often work in, it's allowed. I think we have to be really careful when we put wood fired into these high performance homes of any style, any type, because they'll be so easy to depressurize the house and have backdrafting. Even if it's an airtight stove, you still have to open that to fuel it. And so in some of our work, we've very quickly seen that even just with a dryer running, there's enough negative pressure there to cause a backdraft. And so the house needs a makeup air system if it's going to have a wood-fired fireplace. And so that's just an added cost you need to make sure you're accounting for, and be really careful as you operate a wood burning fireplace in a high performance home. You certainly won't need a very big one, right? Our heat losses are down to 5 kilowatts. What is that? 15,000, 20,000 BTUs, something like that. Lots of fireplaces can't go that low. And so what you'll end up is you'll never be able to have a fire because it'll instantly overheat the house. So it's may not work in all houses.
Yeah, I guess to the cost effectiveness, we want to make sure that our supplementary heat is not costing a lot of money to install and run, where most of these high performance sealed combustion wood stoves are around $5,000 and up, and you still got to install them. So it's a fair amount of money to only have to use it maybe 2 or 3 days a year. It depends what your goals are and whether you're concerned about a grid going down or sustainability or resilience or stuff like that. But if not, just a little 1,500 watt electric heater that costs $20 might cost you another $10 in electricity over its life is probably your most cost effective supplementary heat. But most of the heat pumps, if they're an air source heat pump that's an air handler unit, has a supplementary electric heat built in. So yeah, you can do it. It's kind of the same thing with passive houses. You can do it, but finding one that doesn't overheat the house is tricky.
Yeah, and for backup, we just happened to blow the motor in our fan coil just after completing the walls and windows. And so for like 3 months of that not 3 months, for 3 weeks of that really cold stretch in February, January, we were running on just electric plug-in heaters. And I think we had 2,000 watts between 3 heaters, and that kept our house warm on its own. We definitely couldn't have done that before the renovation if our fan coil had gone down. So that was lucky, I guess, that we had already done the walls and the windows. But you get a sense of how low the heat loss really is, and how little backup heat you might need if the furnace was to go down.
Thank you very much, Tyler. And yeah, maybe we'll have to have you around next year again once we've got all the data, because it's still in progress, but lots of good learnings already.
Yeah, next year we should have even more good, more data, more of the actual numbers for sure. Thanks, guys.
Right.
Thanks for coming.
Thank you very much.
You bet.